Hey, hi all. So today's class we are going to continue our discussion on further topics. So I think from the last two classes we have some drift diffusion and some related problems over there. So that will give you guys a quite understanding of how things is working. So from today's onwards, so let's get started into other topics, like let's extend this into Einstein's relationship. So Einstein's relationship is nothing but a relationship between the constants and the equation of Vt, the voltage relation equation. So how the equation related is the dn, the diffusivity constant of the n-type material divided by mobility of n-type material will be equal to the same, the n-type p-type only differentiated, right? So both we are relating to, which will be equal to Vt. This unit is volt, right? So this unit will also be volt. So this will also be volt. So we know that we can relate the voltage into EV also. So that we related as a KT. So even this is related to EV, the electron volt. Then even we can relate this with the divided by Q. Then E will cancel, right? So this will also be related as a V volt. So the KT by Q, there is another one shortcut formula. So that will be T divided by 11,600 Kelvin. Okay, so this is Kelvin, temperature is in Kelvin. So if we divide by that, we will get KT by Q. So this is one important relationship. So remember this one. So this will give you a very good calculation in many cases. So like the KT by Q or KT or VT at the 300 Kelvin, which will be 23 millivolt. That is a constant value. But if the temperature is varied to 400 Kelvin, then these values will vary. So on the time what you can apply, we can just simply apply 400 divided by 11,000 divided by 11,600. Then you will get some value in a millivolts, right? So that we can let there. So I think this value will be this equation will be helpful when you are trying to solve the problem. So for now, just make a note of it. So Vt is nothing but the thermal voltage. Vt is nothing but the thermal voltage. So Vt is thermal voltage or voltage equivalent of temperature. K is Boltzmann constant. K is Boltzmann's constant. D, as you guys know, D and mu are same. So K value will be equal to 8.63 into 10 power minus 5. The unit will be EV divided by Kelvin K. Then I think remaining things you guys know. So let's get into the other things. Like you guys know this one already. So let me relate some value. So we know that at 300 Kelvin, this is the standard temperature of reference we use in semiconductor device problems. So on the time, if you guys divide 300 divided by 11,000 divided by 600, we will be getting the value of 0.0259. So that will be approximating to 26 millivolt. So this is the standard value we use everywhere. So if they ask any other values like what is the value for 400 and those things, then we can make sure to substitute in this formula and we can find it. So for that's why we need these relationships to be used. I hope this will be understood for you guys. Let me solve one problem that will give you some quite understand. Let's see you guys are remembering the concept or not. So this is one graphical representation where they have given some curvatures. So we already know, right, the curvatures. So that's only they are given. They given two curvature with the E and the side is K. You can call this P or K, anything. So this is A, this is B. Then this is crystalline structure, right? Then what will be the mass equation? Like if option A will be Ma will be equal to Me. There's a both two different substances. Those curvature diagram is given here. Or Ma is greater than Mb. Or option C, Ma is less than Mb. So please pause the video and try to answer it. So if you guys find the answer, please post in the comment section. Let's check what you guys able to do it or not. So here the curvature, we have to compare the curvature. Here the B has more curvature, right? So the mass is indirectly proportional to the curvature. So as we guys already discussed, so mass will be indirectly proportional to the curvature. So from this equation we know that the curvature for the B is somewhat lesser. So mass of A object will be more than the object B. So this is how the answer it will come. So if you guys also able to find it, then I will be happy that you guys are aligned with me in my preparation. Okay, so next let's start with the mass action law. So continuing to this, mass action law is one of the important property in the extrinsic semiconductor and intrinsic semiconductor. So mass action law. So what mass action law states is that the product of free electron and hole concentration in a given semiconductor, the product of free electron and holes concentration, it's not Hp, this is Np. The product of N into P, which is equal to constant value at the constant temperature, and it's always equal to, the constant can be written as Ni square, that is intrinsic carrier concentration. So Ni is nothing but the intrinsic carrier concentration. So intrinsic carrier concentration. Here you can see there is a relationship between the intrinsic and eccentric semiconductor. So that is what this mass action law states it. So it's one of the important formula. So please make a note of it. We will be using this to many other formula derivation, and also in problem we will be using this. So please make a note of it. So at 300 Kelvin, we are having N is equal to P, which is equal to 10. Then what will be the intrinsic carrier concentration? The Ni square, which is a product of N and P. So which will be 100, 10 into 10. Then square root of that will be equal to the Ni, which is equal to 10. So here you see both all are same. So that is the numerics that we take like that. So it's coming like that. So this is how we will be able to find out the intrinsic carrier concentration in some other case. This mass action law is valid only when it is the optimality is same. Like if we consider the case of if there is an 100 donor atom, for an example, let's take a 100 donor atom. So intrinsic semiconductor is a semiconductor. From there we are adding 100 donor atoms plus 100 donor atoms. So donor atoms means it will be n type. So donor atoms added. So then what the thing, the n will be equal to already existing 10 plus 100. So which is equal to 110. Like, but the p which is equal to 10. So the due to recombination, let's take due to recombination. Due to recombination, like whenever there is some electron hole pair generation, there will be some recombination will also happen. So due to recombination, 9 electron hole pairs are recombined. So 9 electron hole pairs are recombined. So recombined. So then what, the n will be 101, then p will be 1. So from this, if n into p, which is equal to 101, so which is prox equal to 100. So here you see this approximately equal to the donor atom added. So in this case only the mass action will be valid. Like what the thing is that the proximity equal to the n into p product that need to be approximately equal to the donor atom added. Means that the doping need to be somewhat optimal, not heavy doping. So mass action law is valid only for the degraded semiconductor. So I will explain the term degraded very clearly in next lectures or coming lectures. For now, note the word that the mass action law is valid mass action is not valid for degenerated semiconductor. Degenerated semiconductor means the doping atom is more than the normal intrinsic carrier concentration. So that's what the term it is saying. So that is degenerated semiconductor. So it's not valid for the degenerated semiconductor, valid only for the non-degenerated semiconductors. So the degenerated in that term we will say that is heavily doped. So degenerated, in the case it is called as heavily doped. So this is heavily doped. So non-degenerated means that is lightly doped or moderately doped. The case that is lightly doped. Okay. So I hope it's very able to understand this concept. So the mass action law validity is very important term. So we can't blindly use this formula everywhere. So we have to make sure that it is follows the necessary principle things. So stay tuned for next lecture. From next lecture we will be getting more into semiconductor physics or electronic devices.